we're going to start with your chemistry of class 12, that is your class 9. And as you know that we had done your 8 classes where we had completed unit 1, unit 2, and even though we had started with unit 3, which is your electrochemistry, and that we had done half of the unit there as well. So hopefully if it is not exceeded, we will end up here only. And first of all, it's a huge request from my side to all the viewers to please go through with the subscribe button and please like, share and subscribe to our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Now we'll go ahead with the topic that we have to discuss today is your electrolyte, that's electrolytic cells and electrolysis that we have to discuss. And we had given some of the solved question we had done and some of the unsolved question that we had done, so that you have to do it. And any problem you will face while solving all these, you can just go ahead with the comment section, so I will provide you the solution for that as well. Let's go ahead. Now we will go ahead and to discuss, as I told you, and that is we'll have to discuss is your electrolytic cells and electrolysis, that we have to go ahead. So in this, that in an electrolytic cells, the external source of voltage is used to bring about a chemical reaction, where the electrochemical processes are of great importance in the laboratory, and that is that the laboratory and the chemical industry. One of the simple electrolytic cell consists of the two copper strips dipping in an aqueous solution of the copper sulfate, and if a DC, which is your direct current voltage, is applied to the two electrodes, then the copper sulfate that the Cu2 plus that ions discharge at the cathode and negatively charged, and are following that we have an equation for that. We have is as follows, which is Cu2 plus aqueous plus 2 that gives Cu as here. So copper metal is deposited on the cathode at an anode, that the copper is converted into Cu2 plus ions by the reaction, and then we'll get the reaction for that is your Cu, it will give Cu2 plus 2e that we have. So thus the copper is dissolved, oxidized at anode and deposited, which is reduced at cathode. This is the basis that for an industrial process in which impure copper is converted into the copper of high purity, and that the impure copper is made an anode that dissolves on passing current, and pure copper is deposited at the cathode. Many metals like Na, Mg, Al, which is your sodium, magnesium, aluminium, etc. are produced on the large scale by electrochemical reduction of their respective cations, where no suitable chemical reducing agent are available for this purpose. Sodium and magnesium metal are produced by the electrolysis of their fused chlorides, and aluminium is reduced, and that by electrolysis of the aluminium oxide in the presence of that is your cryolite, that we'll discuss in the next coming unit, which is your unit 6, we'll discuss there. And after that we'll talk about the quantitative aspects of electrolysis here. Quantitative aspects of electrolysis. So quantitative aspects of electrolysis that we discussed here, where that is the Michael Faraday. Michael Faraday was the first scientist who discovered the quantitative aspects of electrolysis. Now Faraday's law also flow from what has been discussed, that we have discussed earlier. So we'll discuss about the Faraday's laws of electrolysis. So Faraday's laws of electrolysis here, that after his extensive investigations on electrolysis of solutions and melts, of electrolytes that the Faraday published as results during 1883 and 1834. 1833 and 34 in the form of the following well-known Faraday's two laws of electrolyte here, electrolysis here, that we have to discuss. The first we have is the first law. So on the basis of the first law, if I'm going ahead here, detail that the amount of that chemical reaction which occurs at any electrode during the electrolysis and by the current is proportional to the quantity of the electricity that passed through the electrolyte solution or melt here. The second, we have the second law. In terms of second law, that the amounts of different substance that are liberated by the same quantity of electricity that passing through the electrolytic solution are proportional to their chemical equivalent weight, atomic mass of metal that has been divided by the number of electron that is required to reduce the electron as well. Now further we will go ahead. There were no constant current sources that is available during the Faraday's laws here, and that is that the general practice was that to put that colorimeter to that is a standard and that is your standard electrolysis cell, and that for the determining the quantity of the electricity that passing from an amount of metals, and generally the silver or the copper that deposited on the consumed where however we can say that the colorimeters are now of that absolute, and we know how that we have a constant current sources available, that the quantity of the electricity Q that passed is to be given is like in the form of which we have is Q equals to IT, where Q is the coulombs and when I is ampere and T is the second here. So that the amount of the electricity or the charges that required for the oxidation reduction depends on the stoichiometry of the electrode reaction. Example, like in the reaction we have, which is your Ag plus aqueous plus E net, that gives you Ag, that is in solid. So 1 mole of the electron is required for the reduction of 1 mole of silver ions. We know that the charge on 1 electron is equals to 1.6021 into 10 to the power, that is minus 19 coulomb, and therefore the charge on 1 mole of electron is to be equal is like that. We have N1, that is your Na, we can say represented, into 1.6021 into 10 to the power minus 19 coulomb equals to 6 into 0.02 into 10 to the power 23 mole inverse into 1.6021 into 10 to the power minus 19, which will give C equals to 96487 coulomb mole inverse. The quantity for the electricity is called that is your Faradays, and that is represented by the sample, that is Faraday, that is represented by F. For approximate equation we use if like 96,500 Kelvin, that is your coulomb mole inverse for the electrolytic electrode reaction. Then it takes place as Mg2 plus 1 plus 2 give Mg. Yes. Another we have Al 3 plus 3 minus that give Al, that is inside here. For the same case, it is obvious that 1 mole of Mg2 plus and Al2 plus 3 plus that requires 2 mole of electrons, that is 2F, and 3 mole of electrons, that is 3F respectively. So that the charge passes through the electrolytic cells during the electrolysis is equals to the produced of current in amperes and times and seconds. So that is in commercial product of metals, current as high as 50,000 amperes and are used at amount to about 0.518 Faradays per second here. Now we'll go ahead with the question that we have to solve it out here in terms of it, and that is also an important one as well. So on the same cases, the question of the sessions we have here, The question is to be are as follows, like the question is, a solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of the copper deposited at the cathode? That we have to find out. Let's go ahead for the question here. The question is, a solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 ampere. So on the same cases, that is 1.5 ampere, what is the mass of copper deposited at the cathode? So we'll do it the solution for this as well, that is required. So here that is T is equals to 600 seconds, charge equals to current into time, which is equals to 1.5 into 600 seconds, and that is equals to 900 coulomb. According to the reaction, we have that is Cu2 plus aqueous plus 2 electron equals to Cus, that it will give. So we require 2F for our wages. So we require 2F or 2 into 96487 coulomb to deposit 1 mole or 63 gram of copper for 900 coulomb. The mass of copper deposited, which is 63 gram mole inverse into 900 coulomb by 2 into 6487 coulomb mole inverse, that is equals to 0.2938 gram that we have. So this is a solution for this particular question here. Now we'll go ahead with another topic that we have to talk about it, which is about the products of electrolysis, and that is also an important one because all these are playing an important role that we'll talk about it. So on the same basis, we will be going ahead and that we'll discuss about it. Let's go ahead. So the topic we have to discuss is products of electrolysis. So products of electrolysis, if I am going ahead in detail, that is on that the products of electrolysis depends on the nature of the material that being electrolyzed and the type of the electrodes that being used, and if the electrode that is inert, so example like platinum or gold, it does not participate in a chemical reaction and act as only as a source or a sink for electrons. On the other hand, it is the electrode is reactive here, so it participates in the electrode reaction. Thus, the product of the electrolysis may be different for a reactive and inert electrodes. That the product of the electrolysis that depends on the different that is the different which is your oxidizing and reducing species that is present in the electrolytic cell, and their standard electrode potential. Moreover, some of the electrochemical processes, although feasible, that are so slow kinetically that at lower voltages they do not seem to take place, and the extra potential like called that is your over potential has to be applied, which makes such process more difficult to occur as well. For example, if you use molten NaCl, that the products of electrolysis are sodium metal and Cl2 gas. So here we have only one cation, which is your Na plus, which is reduced to the cathode, which is Na plus, that we have as an equation is Na plus, well, like plus electron that gives Na, and one anion that is Cl minus, so which oxidize at the anode, which is Cl minus equals to half of Cl2 plus electron. That during the electrolysis of the aqueous sodium chloride solution that we have, that the products are NaOH, Cl2, H2, and in this cases that besides Na plus and Cl minus here, that ions, we also have H plus and OH minus ions along with the solvent molecules like H2O. So at the cathode there are the competition between the following reduction reaction. The reactions we have is like Na plus aqueous plus electron give NaS. That is, for this we have E, we can say that E of cell equals to minus 271 volt. The another we have the equation is H plus aqueous plus electron is give you half of H2 gas, and that is of E cell equals to 0.00 volt here. So on the same cases, for the reaction with a higher value of E, that is minus, is to be a preferred, and therefore that the reaction is to be at the cathode during the electrolysis. We will be having H plus aqueous plus electron give half H2 gas, and but H plus aqueous is to produce the dissociation of H2O, that is we will get H2O, that is liquid, H plus aqueous plus OH minus aqueous. So therefore the net reaction of the cathode may be written in the form of the sum of these two equations that we will get here is to H2O liquid plus electron will give half of H2 gas plus OH minus. So at anode of the following oxidation reaction that are possible here, which is Cl aqueous half Cl2 gas plus electrode, which is E cell equals to 1.36 volt, and 2H2O liquid that gives O2 gas, and that is plus 4H plus aqueous, and plus 4E, which is E cell equals to 1.23 volt here. So the reaction at anode with the lower value of E is to be preferred, and therefore water should get oxidized in preference of Cl aqueous. So however, on account of the over potential of oxidation reaction is preferred, so thus the net reaction may be summarized as, and that we have the reaction we have is your NaCl aqueous, which is your H2O, Na plus aqueous plus Cl minus aqueous. So there the cathode we have, that is we have H2O liquid plus E minus, that will give half of H2O, H2 which is in the form of gas plus OH minus aqueous. So here anode Cl minus aqueous gives half Cl2 gas plus electron. So net reaction we can say that NaCl aqueous plus H2O liquid will give Na aqueous plus OH minus aqueous plus half H2 gas plus half Cl2 that we have. Now for that, the another one will talk about it in the detail about it, and that we have as follows, that the standard electrode potential are replaced by the electrode potential given by the last equation that take into the account of the concentration effects, and during the electrolysis of the sulfuric acid the following processes are possible at anode here. So that we have as well representing like this. So we'll talk about it as that the standard equation we have, as we had discussed about it as well, which is 2H2O, that is your plus, which is in liquid. It gives O2, which is in the form of gas, plus 4H plus aqueous plus 4E, which is E cell, minus equals to plus 1.23 volt here, that we have to talk about it. So on the same cases here, for the sake that we have to cover up many more things, as I told you, the another equation for the standard that we talk about it, which is 2SO4 2 minus 2SO4 2 minus, which is in aqueous state, plus S2O6, that is 2 minus aqueous, plus 2E minus. So here E minus cell will have equals to 1.96 volt here. So for the dilute sulfuric acid that we talk about it, for the dilute sulfuric acid, that the reactions is to be preferred, but it's harder, that we have a higher concentration of H2SO4 reaction, and that is to be preferred here as well. On the same case, there are many questions related to the in-text question that you have to do by on site, and that we have is your, if the current of 0.5 ampere flows through a metallic wire for 2 hours, then how many electrons would flow through the wire here, and that is suggest a list of the metals that are extracted that is your electrolytically. And the other question is to consider the reaction, which is Cr2O7 2 minus plus 14H plus 6 electron, that gives 2 CRT Cr2 plus 3 plus 7H2 here. So what is the quantity of the electricity in coulombs needed to reduce the 1 mole of Cr2O7 2 minus as well, that we have to discuss here. Now on the same cases we have to go ahead, which is your on terms of talking about the batteries here, and that is also an important one, and another new topic as well. So that let's go ahead to discuss about batteries. Onto the terms of the batteries here as any battery that is that actually it may have one or more than one cell that is connecting in series, or the cell that we are using for a source of electrical energy, that is your batteries galvanic cell, where the chemical energy of the redox reaction converted into electrical energy. However, for a battery that to be the practical use, it should be reasonably that is light and like compact, and its voltage that should vary appreciably during the use. And there are mainly the two types of batteries we have. The first we have is your primary batteries, and the second is your, of course, the secondary batteries. We'll talk about it. So we'll talk about here in the detailed about it. For the first we have is your primary battery, and on the basis of first primary battery we'll discuss here. So in terms of primary batteries, we have to go ahead. In terms of primary batteries, that in a primary batteries that the reactions occurs only once, and after that is used over a period of time, the batteries becomes dead and cannot be reused again. So the most familiar example of this type is the cell that is known as your Leclanche cell, and after its discoveries as well, and which used commonly in our transistors and clocks as well. So where that the cell consists of a zinc container that also act as an anode, and of course the cathode, that is a carbon which we have a graphite that rod surrounded powered manganese dioxide and carbon as well, where that the ammonium chloride, which is NH4Cl, and the zinc chloride, which is ZnCl2, the electrode reaction of the complex are complex, but they can be written approximately that are to be followed at anode. If I'm going ahead, so for anode, which is equals to is your Zn is in the form of solid, it will give Zn2 plus 2 electron, and that is for the cathode. If I'm going ahead, so on that case of the cathode here, which is MnO2 plus NH4, and that we have plus electron, it will give MnO, which is OH plus NH3. So in this reaction at a cathode, the manganese is reduced that from a +4 oxidation state to the +3 state here. So ammonia produced to the reaction that forms a complex here, and with a Zn2 plus to give a ZnNH3 2 plus, that the cell has a potential nearly upon 1.5 volt. And we are in the mercury. If I'm going ahead for a suitable that is for the low current, which we have the devices like bearing aids, and that is another one we have in here, the watches as well, and that is etc., that consists of the zinc zinc and mercury amalgam, that as an anode, and the paste of the HDO and the carbon, and that that as the cathode here. The electrolyte is the paste of the KOH and ZNO, and that the electrode reaction that are the cells as to be given is, and the equation for that anode as well as for the cathode we have. So on anode we have Zn Hg plus 2OH minus, it will give ZNO solid plus H2O plus 2E minus. At cathode, HgO plus H2O plus 2 electron, it will give Hgi plus 2OH minus here. That we have to talk about it. On the same cases, we have the overall reaction that to be represented as, we can just represent in the form of that we have as your ZnHg, that plus HgO solid, that will give ZnO solid plus Hg, which is in the form of liquid here. So here that the cell potential is approximately 1.35 volt and remains the constant during its life, as well as overall reaction that does not involve any ion in solution whose concentration can change during its lifetime as well. On the same case, we have a separator, we have a cathode, we have a gasket as well, and that is here the cell can, anode cap, and anode here. So for that, the secondary batteries will go ahead further to be discussed here, and which is also an important one in reference towards it, that is the secondary batteries. So in terms of secondary batteries here, in this where a secondary batteries cell after use that can be recharged by passing the current through it in an opposite direction, so that it can be used again. And a good secondary cell that we have here, so a good secondary cell can undergo a large number of discharging, and charging cycles. The most important secondary cell is the lead storage battery, and commonly used in automobiles and inverters. So it consists of a lead anode and a grid of the lead packed with lead dioxide, which is PbO2 as anode, and that is a 38% solution of sulfuric acid is used as an electrolyte as well. So the Dell cell reaction when the battery is in the use, that to be given below here, that we have. So on the same cases, we'll go ahead for the anode reaction as for the cathode reaction as well. So on that we have anode equals to, and that we have Pb, that is of solid, plus SO4 2 minus aqueous, give Pb SO4 solid plus 2 electron. For cathode, here that is PbO2 solid plus SO4 2 minus aqueous plus 4H plus aqueous plus 2E, that will give PbSO4 solid plus 2H2O liquid here. So in that is the overall cell reaction consisting of cathode and anode reaction that we have is your Pb, that is of solid, plus PbO2, that is solid, plus 2H2SO4 aqueous will give 2PbSO4 solid plus 2H2O here, that is liquid. So on the same cases, on charging the batteries, that the reaction is reversed and PbSO4 is, and as anode and cathode is converted into Pb and PbO2, that is respectively as well. On the same cases here, which is to talk about it, and that is your the another important here, which is your another important term that we talk about it, which is the another important secondary cell, that is your nickel, and that is your nickel cadmium cells, that which has longer life than the lead storage cell and but more expensive to manufacture. We shall not go into a detail of working of the cell and the electrode reaction during the charging and discharging. The overall reaction during discharge we have, and that is we have as follows, that is your CD, which is solid, plus 2 NiOH twice solid, give CDO solid plus 2 NiOH twice solid plus H2O liquid. So here the next we'll talk about it, which is on terms of fuel cell, that we have to talk about it, and let's go ahead with the same cases for this as well. So we'll talk about the fuel cell here. On terms of fuel cells here, that we have to go ahead, and on the same cases that we have your the production of electricity by the thermal plant, that is not very efficient method and is a major source of pollution, and in such plants the chemical energy heat of the combination of fossil fuels, coal, gas or oil, the first used for the converting the water into the high pressure stream. This is then used to run a turbine to produce electricity. We know that the galvanic cell, that is directly converts the chemical energy into the electricity and is highly efficient, and it is now possible to make such cells in which the reactions are fed continuously to the electrodes, and the products that are removed continuously from the electrolyte compartment. And galvanic cells that are designed to convert the energy of the combustion of we have your, that is your the ends we have, and of the fuels like hydrogen, methane, methanol, etc., that directly into the electrical energy that are called fuel cell as well. One of the most successful fuel cell uses the reaction of hydrogen with oxygen to form water. That the cell was used for providing the electrical power in an Apollo space program, and the water vapor that produced during the reaction were condensed and added to the drinking water supply, or that is for the astronauts. And the cell, hydrogen and oxygens are bubbled through porous carbon electrodes into the concentrated aqueous sodium hydroxide solution. Catalysis like finely divided platinum or palladium metal that are incorporated into the electrodes for increasing the rate of the electrode reaction, and the electrode reactions to be as given flow, that the reactions we have as follows. That will represent it in the form of like that at anode, and that is with we have a cathode as well. So for cathode and for anode as well, so we represent the reaction here as well. So here for the cathode we talk about it, and that is your the cathode we have O2 gas plus 2H2O liquid plus 4E, that will give 4OH minus aqueous. For anode we have 2H2 which is of the gas plus 4OH minus aqueous will give 4H2O liquid plus 4E minus. So the overall reaction for that we have here is your 2H2 gas plus O2 gas, it will give 2H2O liquid. On the case that the cell runs continuously as long as the reactions are supplied, and fuel cells produce electricity with an efficiency of about 70%, that is we have here compared to the thermal plants whose efficiency is about 40%, and there has been the tremendous progress in the development of the new electrode material, better catalyst and electrolysis for increasing the efficiency of the fuel cell, and these have been used in automobiles on an experimental basis, and fuel cells are pollution free, and in view of their future importance, a variety of the fuel cell have been fabricated and tried as well. On the same basis we'll go ahead with the detailed about it, and that is in the terms of we'll go ahead with which we have to discuss about the corrosion as well. So we'll go ahead for the corrosion as well. So in terms of corrosion here, in the same case for the corrosion that slowly coats the surface of metallic object with oxides and the other salts of the metals, and the rusting of the irons, and tarnishing of silver, development of a green coating on a copper, and bronze are some of the examples of corrosion. So it causes the enormous damage of building, bridges, ships, and to all other made of metals, especially that of iron, and we lose crores of rupees every year on account of the corrosion here. In corrosion, a metal is oxidized by loss of electron to oxygen and formations of oxide. The corrosions of irons, commonly known as rusting, and occurs in presence of water and air. The chemistry of the corrosion is quite complex, but it may be considered essentially as an electrochemical phenomena, as a particular spot of an object that made of So in terms of the corrosion, in corrosions, a metal is oxidized by the loss of electron and to oxygen and formations of oxides, and corrosions of iron, that commonly known as rusting, that occurs in the presence of water and air, and that is the chemistry. In the chemistry of the corrosion is quite complex, but it is maybe considered essentially as an electrochemical phenomena at a particular spot of an object that made of iron. An oxidation takes place and that spots behave as anode, and we can write the reaction as well. For that anode we'll talk about it, and that we have 2 Fe. Yes, that will give 2 Fe 2 plus 4E minus, which we have E cell equals to, which is Fe2 plus slash Fe, that we have minus 0.44 volt here. On the same cases, for the electron that release at anodic spot, that move through the medical metals and go through the another spot on the metals and reduce oxygen in presence of H plus, and which is believed to be available from H2CO3 that formed due to the dissociation of carbon dioxide from air into water, and hydrogen ion in water that may also be available due to the dissociation of the other acidic acid oxides from the atmosphere. The spot that behaves as cathode with the reaction that we have to talk about it, and that for the cathode we have here as follows. For the cathode equals to, that is your O2, which is in the form of the gas here, and that we have plus 4H plus aqueous, 4E minus, that we have 2H2O, and liquid. So for that we have E cell equals to 1.23 volt here. For the another one we talk about it, which is the overall reaction, we have 2Fe solid plus O2, which is in the form of gas, plus 4H plus aqueous will give you 2Fe 2 plus aqueous plus 2H2O liquid here, and that is E cell we have equals to 1.67 volt. So the ferrous ion are the further oxidized at atmospheric oxygen to the ferric ion, which comes out to the rust in the form of the hydrated ferric oxide, which is Fe2O3 xH2O, and with the further productions of hydrogen ions as well. Where in the same case that the prevention of the corrosion is of prime importance here. It is only the saves money, but also helps in preventing the accidents such as like bridge collapses, but also helps in preventing the accidents such like bridge collapse or failure of the key component due to the corrosion. One of the simplest method of preventing the corrosion is to prevent the surfaces of the metallic object to conduct here that the contact with the atmosphere. This can be done covering the surfaces with the paint or by some chemicals. An example is your bisphenol and phenol, and that is the another simple method is to cover the surface by the other metal like Sn, Zn, etc. that are inert or react to save the object as well. An electrochemical method is to provide a sacrificial electrode of another metal like Mg, magnesium, zinc, etc., and which corrodes itself but saves the object as well. On the same cases, we'll talk about that some of the questions here that I will give you as in homework. Right, write the chemistry of the recharging the lead storage batteries, like highlighting at all the materials that are involved during the recharge. And the other way we have suggest two materials other than the hydrogen that can be used as fuels in the fuel cells, and another is to explain how rusting of the iron is in a visage on setting it up on an electrochemical cells as well. On the other cases we go ahead that we'll talk about the hydrogen economy here. In the terms of hydrogen economy, that is also an important one, so that we have to discuss here. So just I will let you know. The hydrogen economy. So in the cases of the hydrogen economy, if I'm going ahead, at present that the main source of the energy that is driving out our economy is a fossil fuels such as coal, oil and gas. As more people on the planet aspires to the improve then the standards of living, their energy requirement will increase. In fact, that the per capita consumptions of energy used in the measures of development, and of course if it is assumed that energy is used for productive purposes and not merely wasted. We are already aware that the carbon dioxide produced by the combustions of the fuel that fossil fuels is resulting in the greenhouse effect, and this is leading to rise in the temperature of the earth's surfaces, that causing the polar ice to melt and the oceans levels as well to rise as well, and this will flood low-lying areas along the coast and some in Iceland nation such as Maldives face the total submergence, and in order to that we avoid the such catastrophic, and we need to limit our use of the carbonaceous fuel, and hydrogen provides an ideal alternative as its combination results in water only. Hydrogen production that must come from the spreading water using the solar energy, therefore the hydrogen that can be used as a renewable and non-polluting sources of energy. This is a vision of the hydrogen economy, both the production of the hydrogen and electrolysis of the water and hydrogen combination in the fuel cell that will be the important in the nature, and both these technologies are based on the electrochemical principle as well. So on the cases we have, we all write the Nernst equation of the EMF of the following cells that are 298 Kelvin here, and that we have to talk about it, which is Mg2 plus, and let me talk about it. And for the reaction we have here, there are many reactions for the Mg, Fe, Sn and Pt here. And for that, in the button cells that widely used in the watches and the other devices, that the following reaction take place. So the reaction we have for that is your Zn solid plus Ag2O solid plus H2O liquid will give Zn2 plus aqueous plus 2Ag solid plus 2OH minus, that is aqueous here. Determine the delta R of G and E minus that we have here, and that we have to talk about it for the reaction as well. And here that you have to define the conductivity and the molar conductivity for the solution of the electrolyte and discuss the variations with concentration. Then other is to the conductivity of 0.20 mole solutions of KCl at 298 Kelvin is your 0.0248 as centimeter inverse, and calculate this molar conductivity as well. The resistance of the conductivity will containing 0.001 mole KCl of solution at 298 Kelvin is 1500 ohm. What is the cell constant if conductivity of 0.001 mole KCl solution at 298 Kelvin is 0.14 into 10 to the power minus 3 as centimeter inverse as well. Now we'll talk about for the another one that we have to go ahead as well, and that is on the same cases. We have many more questions. That is the conductivity of the sodium chloride at 298 that has been determined at the concentration and the results that have to be given here. And the conductivity of 0.00241 m acetic acid is 7.896 into 10 to the power minus 5 s centimeter inverse. You have to calculate the molar conductivity and lambda m naught, and that is for the acetic acid 390.5 s centimeter square mole inverse as well. And what is the dissociation constant, you have to find out. The another we have is how much the electricity in terms of the Faradays is required to produce. And another is that a solution of NiNO3 twice is electrolyzed between the platinum electrode using a current of a amperes for 20 minutes. A watt mass of Ni is deposited of the cathode as well. Another is three electrolytic cells ABC containing the solution of ZnSO2, SO3, AgNO3 and CuSO4 respectively, that are connected to in series, and a steady current of 1.5 amperes was passed through them until 1.45 gram of the silver deposited at the cathode of the cell B. And how long did the current flow, and what mass of the copper and the zincs were deposited as well. The another will talk about it to predict the product of the electrolysis in the equation, and using the standard electrode potential we have to predict the reactions between the following. It's feasible like FPAG, Fe2 plus and Ag as well, and then PR2 as well. So that we have to discuss here, and here we'll end up with, and we'll discuss in the next coming class, that is your the chemistry, that is the another one which we have is your another chapter we'll have to discuss, which is your chemical kinetics. And in terms of chemical kinetics, that is also an important one here. In terms of chemical kinetics, if I am going ahead, that we have to discuss as well. First of all, it's a huge request from my side to all the viewers to please go through with the subscribe button, and please like, share and subscribe our channel, so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. And other than chemistry, if I'm going ahead, we had done your sociology whole, and we had started with unit 1, it's software engineering, which we had completed unit 1, unit 2, unit 3, unit 4 as well, unit 5 as well. We have to do the solution the question paper here as well, that will deal hopefully in the next coming class. And after that, we are dealing with the quantitative aptitude, where arithmetical ability may be how many operations on numbers, logic, that is your LCM and SCF of numbers, and decimal fraction and simplification, that we are dealing with the fourth topic here. And in terms of reasoning here, we had completed the verbal reasoning, which is general mental ability in the logic reasoning. And in terms of non-verbal reasoning, we had completed more than 1000 questions of the series, as well as we had done your that is your 500 question for analogy, classification, analytical reasoning, and we are dealing with the mirror image, and hopefully in the next coming class we'll end up with that as well. While talking about the chemistry here, if I'm going off, this has been your class 12th chemistry, which is important for the academic and competition as well. Here we had completed unit 1, which is the solid state, where we had completed the general characteristics of the solid state, amorphous and crystalline solid, classification of crystalline solid, crystal lattice, and unit cells, numbers of the atoms that we have in a unit cell, and a closed packet as structure, packing efficiency, calculation involving the unit cell dimensions, imperfections in solid, electrical properties, magnetic properties as well. Unit 2, we had completed the solution, that is type of solution, expressing the concentration of the solution, solubility, vapor pressures of the liquid solution, ideal and non-ideal solution, colligative property, and the determination of the molar masses, abnormal and molar masses as well. Unit 3, which we had completed in this state, that is electrochemistry, which is electrochemical cells, galvanic cells, Nernst equation, conductance of electrolytic solution, electrolytic cells and electrolysis, batteries, fuels, and as well as the fuel cells, and the corrosion we had done here. In next coming class, we'll start with discussing about the chemical kinetics, which we have to discuss the rate of the reaction, factor influencing the rate of the reaction, integrated rate equation, pseudo first order reaction, temperature dependence on the rate of the reaction, collision theory of the chemical reaction as well. That unit 5 we have to discuss, that is the surface chemistry, adsorption, catalyst, collides, classification of collides, emulsions and collides around us. Unit 6, general principles of the process of the isolation of element, which is occurrence of metal, concentration of ore, the extraction of crude or metals from the concentrated ore, thermodynamics, principle of metallurgy, electrochemical principles of metallurgy, oxidation, reduction, refining, uses of the aluminium, copper, zinc and iron. Unit 7, the P block element, which is group 15 element, dinitrogen, ammonium oxides of nitrogen, nitric acid, phosphorus, allotropic forms, phosphine, phosphorus halides, oxohalides of the phosphorus, and group 16 element, dioxidation, simple oxides, ozone, sulfur, allotropic forms, sulfur dioxygen, oxoacids of the sulfur, sulfuric acid, group 17 elements, chlorine, hydrogen, chlorine, oxoacids of halogens, interhalogens compounds, group 18 elements as well. The another we'll have to discuss is your unit 8, which is your DNF block element, which is the position of the periodic table, and electronic configuration of the D block element, general properties of the transition element of the D block, some important compounds of the transition element, the lanthanides, actinides, and some application of D and F block elements as well. Last unit we have to cover up is your unit 9, which is the coordination compound, where we have to discuss about the oneness theory of the coordination compound, definitions of the some important terms pertaining to the coordination compound, nomenclature of the coordination compound, isomerism of the coordination compound, bonding to the coordination compound, bonding to the metal carbonylysis, stability of the coordination compound, importance and application of the coordination compound here. So here we'll thank you, and I hope you enjoyed this video. If you like this video, please give a thumbs up and give a suggestion and comment box. Please like, share and subscribe our channel, so that many maximum people can get the information at once, and even you can also enjoy the video as well. So thanks for supporting us, and thanks for subscribing us. Thank you.